All right, welcome to our last section, section 3.5, ending out chapter 3. We're going to be going back to something that we covered sort of just briefly earlier on in the chapter. So one of the most easily understandable situations most frequently modeled by exponential functions, talking about sort of an application here, is compound interest. Compound interest formula is A equals PE to the RT. So we talked about this. This is for continuously compounded interest, where P represents the principal, R represents the rate, T represents time, and A represents the balance. You think of that as like the current amount. So I'm just going to do these two slides, or this slide of two examples. How long will it take to double $500 at a rate of 5% compounded continuously? So P, the amount of money that I'm putting into this is $500. R is 0.05 because you have to remember that I moved that sort of decimal over 2 spots. And then the other piece of information that we know is what A is. We know what A is because what we're asking is how long will it take, so we're looking for T, in order to double $500. Well, doubling $500 means that I would have $1,000. So if I use that formula, A equals PE to the R times T, I get 1,000 equals 500 E to the 0.05 T. If I divide by 500 now, I can't divide by E because it's not E times T. So I get 2 equals E to the 0.05 T. Now, this 2, just to sort of think about what that 2 represents, that 2 represents the ratio of the actual amount in your account over how much you put in. So that 2 is representing the fact that it's double. So now if we're looking at this equation, we have to use our chapter 3.4 skills to solve this. Because if I want to get rid of E, what I need to do is introduce natural log on both sides. So that here it cancels, and I'm left with the natural log of 2 being equal to 0.05 T. So now I can divide by 0.05. The exact answer then is T equals natural log 2 over 0.05. The approximation for that, because in this case the approximation makes more sense, would be something like 13.86 years. All right, after 10 years of investment at 3%, you have $5,000. What was the initial investment? So T is 10 years. The investment rate was 0.03 or 3%. And it's after 10 years, I now have 5,000. So what has been given to me is the amount of money I currently have. And I don't know what P is. So 5,000 equals PE to the 0.03 times 10. It's the same as 5,000 equals PE to the 0.3. I just multiplied those. Now, if I'm trying to solve for P, I don't need to introduce natural log in this case because I'm not trying to get rid of the exponential function and be left over with just the exponent. The variable isn't in the exponent. You have to look at the fact that really what I have here is P times E to the 0.3. E to the 0.3 is just a number. We could put that in our calculator. Or we can just say we're going to divide by E to the 0.3. So I get P is equal to 5,000 over E to the 0.3, which again, that is the exact. It doesn't really make too much sense. It comes out to approximately $3,704.09. So important here to realize the approximation was more important. And also sort of keep in mind whether or not your answer makes sense. I initially put in $3,700. And now I have 5,000 after 10 years. That makes sense. Sometimes what I'm going to get for an answer for something like this is like 12,000. So you're saying that I put in $12,000 and now I have 5,000, but it was an investment and I was somehow losing at a constant rate. All right. Moving along a little bit, we're just going to do 2 more slides. So radioactive decay. Decay is going to work almost the exact same way, except that the rate is going to be negative, which would indicate that it's a decreasing function. Oftentimes, the half-life of an element is given to represent its rate of decay. So our half-life formula is 1/2 equals e to the RT. Because we're saying that we have half the amount that we usually did. Other ways that you could be writing this, 1 is equal to 2e to the RT. 1 representing I currently have 1 if I initially put in 2, because now it's half. Or natural log of 1/2 equals r times t. You notice if I just put natural log in front of these, I would get natural log 1/2 equals RT. So what is the rate of decay for an element with a half-life of 500 years? So T here is going to represent the half-life. So I would have 1/2 equals E. I know that T is 500, and I'm looking for R. I get natural log 1/2 equals 500R. So I divide by 500. So R is equal to natural log 1/2 over 500, or approximately negative 0.1%. And, to get that approximation, you're just putting that into a calculator. Now, with that previous rate, that negative 0.001386, again, this representing negative 0.1%, how much would remain of 15 grams of an element after 1,000 years? So this is where people get a little bit tricked, because in this case, what they then go and do is they use the half-life formula. But it's not looking for when is it going to have half of the original amount. Half-life formula we use in order to get the rate of decay. Now I'm just going to use my regular A equals PE to the RT, but I now have that half-life rate. I want 15 grams to remain. I want to initially put in 1,000 grams. R is representing that negative 0.001386 times T, and I'm looking for T. I'm sorry, I'm not looking for T. I did this wrong. Totally ignore part of that. You could, hate me, come in, yell at me, hate me. Sorry, 1,000 years. I was doing a totally different question. It wants to know how much will remain. So we don't know what A is. The amount we're putting in is 15. We have E to the negative 0.001386 and 1,000 years. Okay, so this is a lot more easier of a question because you just pop that right into a calculator. You get A is approximately 3.75 grams. Again, you think about whether or not this makes sense, and this does make sense. I started off with 15 grams. I'm talking about decay. I now have 3.75 grams. That's logical. All right, jot down if you have any questions. I think I just have 2 other slides and I'm going to do in the examples, so that will go relatively quick as well.